All right, so first question for today. If it takes a boat captain whose boat points straight ahead, which is due east at all times, 20 seconds to cross a 400-meter wide river, what's the velocity of the boat with respect to the water? This is one of those problems where you got to remember that horizontal and vertical have to be separate. Which one matters for this problem? Yeah, horizontal. Does that velocity of the river matter here? Doesn't matter at all. So what we want to do is go to another slide. We know that the river is 400 meters wide. So that's the displacement he has to make. And we know that it takes him 20 seconds to do that. We want to find the boat's velocity with respect to the water. That means how fast is the boat going if the water's not moving. And all we're going to do is just use one of our favorite equations. Delta x, I wrote that wrong. Delta x equals dt. And we want to solve it for v. So v equals delta x divided by time. So the guy's going 400 meters, and he's doing that in 20 seconds. So I'm hoping you figure out his velocity is 20 meters per second. 20 decimal point 0 meters per second. All right, and we should throw on what else there? East. Does that make sense? Again now? Well, since the question said due east, I probably wouldn't count off. But it's better to go ahead and just tack on the direction. Because it does ask for a velocity. So you could tack on east, or you could just draw an arrow and going like that. Everybody okay with that one? Keep horizontals and verticals separate. Key thing. So let's back up and look at the second part. The resultant velocity is what we're looking for in question 2. That means we need to add together what? The 20 east and the 4 south. So again, he's going 20 meters per second due east, and the boat's going 4 meters per second straight south. So we'll draw those tip to tail. Drawing our resultant from where we started to where we got through. Call that R. And just do some Pythagorean theorem work. So R squared is going to equal, this will be 416, right? 416. We need to take the square root of that. 20.4 meters per second. Now remember, we're asking for resultant velocity, not resultant speed. If we ask for speed, that's what we need, right? 20.4. But we need an angle because we asked for velocity. The angle we want to give is the smallest angle between our resultant and the horizontal, east-west horizontal. So find that angle. Easiest way to do that is just say tangent. So we'll say the tangent of our angle theta is opposite over adjacent. We'll divide that out and take the inverse tangent. So that's 11.3 degrees. We would say 11.3 degrees south of east. Start at east and go south 11.3 degrees. Everybody okay with that? All right, well, let's look at one more part of this one then. How far downriver, how far south will the boat be when it reaches the other side? Well, there's only 2 things we really need to know to work this part. How long does it take him to go across the river? 20 seconds. And how fast is he going down the river? 4 meters per second. So this is just another one of those delta x equals dt problems. So we're going to say the velocity, the only velocity that matters down the river is the velocity of the river. So v is 4 meters per second. And the time across the river is the same amount of time it goes down the river, that's 20. Seconds cancel out. So we're at 80 meters down the river. Sound good? Yeah, you probably should just say 80 meters, put an arrow on there, or down the river, or due south. Any one of those would be okay. But you do need to tack on a direction. All right, I'm going to pause the recording here for just a second. All right, so second problem, we're firing a cannonball. We're firing it up at 45 meters per second at an angle of 50 degrees above the ground. And we want to know how long it's in the air, what's its range, and what's its maximum height. Whenever you do a problem like this, the very first thing you got to do is what? Break it into components. So let's do that first. Remember what we're doing is we're shooting our ball 45 meters per second at a 50-degree angle above the ground. So we're going to draw in a vertical. I like to call this V and this H. And we're going to find those two components of our velocity. So to find the H, we'll use cosine. We'll say the cosine of 50 equals our adjacent side over our hypotenuse. And we'll say the sine of 50 equals our opposite side, V, over our hypotenuse. So we'll calculate that out real quick. This horizontal component comes out to be about 28.925. And again, carry out a couple of extra significant digits until the end, a couple of extra digits until the end, and then round it. So I'm going to go 50 sine times 45. And my vertical component is 34.472. Remember, this one's going this way, and this one's going that way. The next thing you've got to remember on a problem like this is which one determines your time in the air. The vertical. So forget the horizontal one's even there. Just think about this problem as if you threw the ball straight up and then it came straight back down. Because it's going to work the same way. The math works the same way. Just think vertical. So if we're just thinking vertical right now, our VI is 34.472. What's our VF going to be if we're just thinking vertical? Negative 34.472. That's what you meant, right? Yeah, at the maximum height, it'll be 0. And our acceleration is going to be negative 9.8. So our good old VF equals VI plus AT equation will work here for us. So we'll go VF equals VI plus AT. Solve that thing out for T. So T is going to equal VF minus VI all over A. And then it's just a matter of plugging in from there. So we'll go negative 34.472 minus 34.472, all divided by negative 9.8. All our units cancel out except seconds. Makes sense. We're looking for time. So when we work this out, we need 3 sig figs. Our time comes up to be 7.04 seconds. And that's the answer to the first part. Everybody okay with that? All right, let's back up and look at what the second part was. The second part is we're going to find the range. And remember that range is the horizontal displacement. And that is completely dependent on which component? The horizontal component. So 28.925 is our horizontal component. I'm going to go to a different slide so we have some space. So our horizontal component of our velocity, I'll write it as VH, was 28.925. And that's how fast we're going sideways. And how long did it go? 7.04 seconds. So we're just looking for a displacement. The range is the horizontal displacement. So we're going to say delta x sub h, horizontal displacement, equals VT. Because what do we know about that 28.925? What do we know about the horizontal component of velocity in a projectile problem? No, it doesn't change because there's no what acting on it. No force. The only force acting is the vertical force of gravity. Doesn't affect the horizontal velocity. So just go VT, 28.925 times 7.04. Multiply that out. We had 3 in our initial problem, so we need to stay with 3. So 204 meters. And it's always a good answer just to put a direction on there, so I'll just put sideways. Questions there?
203.
It's just a rounding thing. That's okay. I got a little bit more probably because I carried out some extra digits. Did you carry out that many digits?
I carried more than that, but you guys said.
Always a good idea to carry out a couple of extra digits past your sig figs. All right, I'm going to leave the time up here. We still need to do part C. Part C was the maximum height. We know the maximum height is completely dependent on the vertical part, right? And our vertical component, 34.472 meters per second. So let's go back to that next slide. We're starting off with an initial vertical velocity of 34.472. At our highest point, what's the final velocity? 0. Get us up there and it stops. We got an acceleration of negative 9.8. And that's about what we know, right? We're trying to find the vertical displacement. There's a lot of different equations we could use to find it, but probably the easiest one is going to be this. Now, where a lot of you messed up on the last quiz is you put in 0 for VF, which you should have. Most of you put in 34.472 for your initial velocity, but your time, you plug in the 7.04. That's the time up and the time down, right? That's not what we need. We just need the time up. So we're going to go 7.04 divided by 2 and get 3.52 for our time. I'll give you one in a second. Let's go ahead and multiply this out. So let's go 34.472 times a half times 3.52. And we end up with 3 sig figs, about 60.7. That's meters up. Does that make sense? All right, again, I'm going to pause our recording for a second. All right, guys, so the next problem we're going to work is number 8 up here. We want to add 2 vectors that aren't at 90 degrees with each other. And whenever you do that, what's the first thing you've got to do? You've got to break them into their components. They're north-south, east-west components. So let's go to a slide where we can do that. But the two vectors we're trying to add, 65 newtons, 35 degrees south of east, and 32 newtons, 45 degrees north of west. Trying to sum those up. So here's a blank slide. First thing that we want to do is just draw both those vectors out. So 65 newtons, 35 degrees south of east. So we'll draw that like this. 65 newtons, and our angle here is 35 degrees. Let's go ahead and draw the other one over here too. This one is going up like this. It's going north of west, 45 degrees, 32 newtons. So like we said before, the first thing that you want to do is break these into components, do vector resolution. So let's draw down a vertical. And let's find our, I'm going to call this N since it's to the north, and I'm going to call this W since it's to the west. And I'll use sine and cosine. And the nice thing about this one, since it's 45, what do we know? Both the components are going to be the same, right? 45 degree angle. So we're going to say sine 45 equals north over 32, and cosine of 45 equals west over 32. Calculate that out. Our components on this one come up to be 22.627. And both of them will be that. Remember, this one's going to the north and this one's going to the west. On our other picture over here, same thing. Find our components. Sine of 35. Well, actually, let me draw in the vertical first. This component's going south. This one's going east. So I'll use sine to find the south component. And I'll use cosine to find the east component. Calculate those out. All right, the south component comes up to be, I'm going to write it up here where I have a little space, 37.282. Remember, that's going to the south. And then the other one, the east component, 53.245, and that's to the east. So again, when you're adding two vectors that aren't at 90 degrees to each other, find the components, the vertical and the horizontal components. Then what do? Well, you combine the north and the south components together, and you combine the east and the west components together. Yeah. So our problem was in number 8. Good?
So you're finding opposites, and you're right to the sides that gives you the south and east, so you're finding, because we found the north and the west.
No, we found the north and the west on the second one. We found the north and the west on this one. We found the south and the east components of this one. I did them in the opposite order that they were written. All right, so now let's take our north and south components and combine them. We've got 22.627 north, and we have 37.282 to the south. So this thing's going to go to the south, right? So let's go 37.282, and let's subtract from that the north, because they're going in opposite directions. So minus 22.627, and we end up with 14.655 newtons south. So that takes care of this. And it takes care of that. And those are now combined to each other. And now let's take the east and the west components and combine them. So we've got that going west. We've got that right there going east. So east is going to win this competition. So let's go 53.245 minus 22.627. And we end up with 30.618 newtons east. So far what we did is we broke our vectors into components. We combined north and south and east and west. Now what do we got to do to finish this up? We got to find the resultant. We got to do a tip to tail triangle. So I'm going to erase a little bit here, make some space to do that. That ought to work. So we'll just take our two combined pieces, these two. So we've got a 30.618 east, and we're going to draw that tip to tail. Did I put my arrow on this one backwards? Was that south or north? South. So that's newtons. Newtons south. So it's 14.655. So we want to draw in our resultant, which will be right here. Do some Pythagorean theorem. So our east component plus our south component. Go ahead and calculate that out. That comes up to be 33.9. And that's newtons. But we've got to find an angle because force, just like velocity, is a vector. So the angle we need is that angle right there. Smallest angle between our resultant and our horizontal. So use tangent. And just say the tangent of your angle is opposite over adjacent. So divide that out. Take the inverse tangent, 25.6 degrees. And that would be south of east. And remember, that means start at east and go 25.6 degrees toward the south. Any questions on that one? Not difficult, just time consuming. This one's just kind of time consuming. Not hard at all, just takes a while. All right, now this is a problem you haven't seen one exactly like before. We're going to go ahead and work through this one together. Take a minute and read it. Say again? Yeah, this one's out of the book. You have it's pretty much exactly out of the book, this one is. A spy, so this is like a James Bond problem. A spy in a speedboat is being chased down a river by government officials in a faster craft. Just as the official's boat pulls up next to the spy's boat, both boats reach the edge of a 5-meter waterfall. If the spy's speed is 15 meters per second and the official speed is 26 meters per second, how far apart will the two vessels be when they land below the waterfall? This sounds kind of complicated. This is actually maybe the easiest problem that we've done so far. Let's think about it on a blank slide here. Here's what we got. Let's think this is a waterfall. I'm just going to draw an X here for one of the boats. We're going to do one boat at a time. We'll do James Bond's boat first. He's going 15 meters per second. And he's going off this cliff that's 5 meters tall. What do we got to know about James Bond?
He can kill anyone.
We got to know the time, and eventually we've got to find the range, right? The horizontal distance. we know that his path, his actual path, is going to look something like half of a parabola, right? We need to know this distance. We'll call that the range. But what always determines our time? The vertical stuff. What's he start out at vertically in terms of velocity? 0, because he's coming off horizontally, right? He's coming off the cliff horizontally. So just thinking vertically right now, VI vertically 0. Acceleration, negative 9.8. What else do we know vertically? We know his displacement. It's negative 5 meters, right? He's got to fall 5 meters vertically. And you do need to make that be negative or your signs are going to look a little weird. He's falling. Make it be negative. So probably the easiest equation to use here would be delta x equals VIT plus 1/2 AT squared. The nice thing in this case is that VI is 0. So that goes away. So we've got delta x equals 1/2 AT squared. Let's take a minute and solve that out for t, because that's what we're going to have to find first. So we'll multiply both sides by 2. And that'll give us this. We'll go ahead and divide both sides by 8. And then we'll take the square root of both sides. So that's the equation we're going to be working from right there. We know all those variables. So we'll go 2 times negative 5 divided by negative 9.8. Take the square root of all that. And that will give us our time. And once we find this time, that's going to be the time for both boats, right? They're both starting off at 0 vertically. Time's going to be the same. So let's go 2 times negative 5 divided by 9.8 square root 1.01 seconds is what I'm coming up with. All right, so if we're thinking about James Bond here for a minute, James Bond's going how fast horizontally? 15. That doesn't change, right? So let's go delta x equals dt, 15 meters per second, times 1.01 seconds. So he goes 15.15 meters. Now the other boat was going how fast? He was going 26. Well, he goes 26 meters per second for the same amount of time. And 6.26, exactly. So this is how far from the cliff the second boat reaches, 26.26. This is how far James Bond reaches. The question asks us how far apart are they? So let's just subtract those two, right? So let's go 26.26 minus 15.15, and we get 11.11. We need 3 significant digits in this problem, so just 11.1 meters apart. Anybody have questions on that one? That was pretty easy, right? Takes a little time, pretty easy. All right, now this one is pretty much just like one off the quiz. Take a second and read it. This is the one where you kind of had to think a little bit. But if you did the correct logic, this one was a really easy problem. Problem about Ben flying his jet. So this time he wants to go due north. The wind's pushing him west. So let's go to a slide and think about what we need to do here. Ben wants to go due north. The wind is pushing him to the west, which means Ben actually has to fly which way? North, east, right? So he's got to go that way so that he'll end up straight north, because the wind is pushing him toward the west. Now, here was the key thing. He wants to end up going due north 425 meters per second. The wind is pushing him 85 meters per second that way. The big piece of logic that you got to make here is that if we break his initial velocity into components, what do we want this component right here to end up being? 425, right? We want him to end up with that. And what does this component right here have to end up being? 85 to the east, so it cancels out what? The wind. So this has got to be 85. So essentially now all we've got to do, this is what we're looking for. We're looking for how fast did he have to go and what angle did he have to go at. So we need this side and we need that angle. So it's just Pythagorean theorem and tangent again. So r squared equals 425 squared plus 85 squared.
You know what this was?
Do what now?
Number
12 I think is right. So 425 squared plus 85 squared, and these are different. These are different numbers than in the problem. Do the math on this. R comes up to be 433 with the 3 6 that we need. We need an angle. And again, the angle we want is the angle between our resultant and our horizontal, our heading angle. So tangent. So we'll say the tangent of our angle equals opposite over adjacent. Take the inverse tangent of that. 78.7 degrees. And that would be 78.7 degrees north of east. How's that look? Everybody okay with that? You understand how to get the direction now? Okay, let's look at one or two more. This is the tough one right here.
No.
This was the bonus question that I gave you last night. Told you it was kind of a doozy to work. It is. This is one where you're going to have to use two equations, solve for one variable in one equation, substitute it in another. Take some work. It's not impossible. It's a really common type of physics problem. So make sure you know what the problem is first of all. So we're hitting this golf ball up at a 34-degree angle. It lands 240 meters down the range of a level golf course. We want to know its initial speed. We also want the max height. The max height will be easy. The hard part to find is going to be that speed. So let's think where we're going to start. That 240, that's the range, right? And the range is the horizontal displacement. And how do we usually find horizontal displacement of a projectile? VT, right? Horizontal speed doesn't change. VT. We'll come back to that in a second. Here's what we know. We know that we're shooting this thing up at a 34-degree angle. Now here's the tricky part. We're actually looking for what that speed right there is, right? That's what we're looking for. We don't know it. Told you a minute ago that we're going to have to do two equations and solve and substitute. Because up here, we don't know V or T. correct? All we know is R. I'm going to draw down a vertical right here, break this into components. I'm going to call this my horizontal component. And since I've already called this V, I'm going to call this U, my up component. Break it into components like I would normally do. Say the sine of 34 equals U over V. I'm going to go ahead and solve that out for U. My up component would be V times the sine of 34. And then I'm going to do the same thing with the horizontal. I'm going to say the cosine of 34 equals H over V. Solve that out for H. All right, now V is what I'm actually looking for, correct? The initial velocity of the ball. Let's go back up to my range equation for a second. This V right here, down here is which one of these things? It's got to be the H, right? So I'm going to go up here and instead of writing VT, I'm going to write cosine 34 times V times T. Now I've got to find T. And what always determines your T? Vertical stuff. So let's think about vertical stuff for a minute. We know this. We know that this ball is going to leave the ground and it's going to come back to the ground. So what does that tell us about the ball vertically? If it leaves the ground and it comes back to the ground. The displacement's 0, right? It goes up, it comes back down, it's where it started. We know the acceleration. So here's what I'm going to think about. We're going to think about this equation right here. Delta x equals VIT plus 1/2 AT squared. What's our displacement vertically? We just said it. 0. The VI that I've got written there, what would that be in terms of the problem that we're working right now? What would that VI actually be equal to? We're talking vertically, so the VI would have to be this right here, right? The initial vertical velocity, that's what that is. So let's plug that in for VI. V sine 34 times T plus A is what? Negative 9.8. So I'm just going to go ahead and go 1/2 times negative 9.8 and get 4.9. Everybody with me on what I've done there so far? I'm going to subtract the V sine 34t from both sides. We'll go ahead and divide both sides by t to get rid of that. So you got t's on both sides. So if I divide both sides by t, this goes away. And that square term goes away. And now I can just divide by negative 4.9 to get t. And what happens to my negative signs? Got negative, negative, so those go away. So now I got t. Now what can I do with that? I can take it and substitute it in up there. And that's going to get me down to what? One variable. The only variable that I'll have left is v, which is what I'm trying to find. So I'm going to make a little space so that I can do this, because it's going to take a little space to work. Let's go ahead and plug in what we know. What do we know the range is in this problem? It gave us that, right? Told us it was 240 meters. So I'm going to say 240 meters equals v cosine 34 times t. But I'm going to put this in for this t right here. So v cosine 34 times v sine 34 all over 4.9. I've got to do a little algebra here, but it's doable. What do we need to do first? Yeah, go ahead. Well, because you're multiplying by 4.9, so when you multiply it, you could just write it. I mean, you could just write the 4.9 on this side, but you're multiplying by it, so it's the same thing. It doesn't matter. Where's what come from? That was the range that was given to us in the problem. It is confusing, I know. But what we've got to do now is we've got to, this was meters per second squared. We need to multiply both sides by 4.9. So we'll have 240 meters times 4.9 meters per second squared equals v cosine 34 times v sine 34. Multiply that out. That gives us 1176 meters squared over second squared equals, I'm gonna rearrange the other side just a little bit. We could write that v squared, right? Because it's v times v. V squared sine 34 cosine 34. Now, this is not so bad from here on out. What do we got to do now is just divide both sides by what? Sine and cosine of 34. Just divide both sides by sine and cosine of 34. So that goes away on this side. So now this is a doable problem. We just need to go 1176 divided by the sine of 34, and then divide it again by the cosine of 34. And then we need to take the square root, because that's v squared. It's equal to v squared. So take the square root, and we get around 50.4. Yeah, I just derived the equation because I wanted you to see where that equation came from. So we just derived it out. Now, what that is, this 50.4, remember, the way the problem started is we shot the ball up at a 34-degree angle. This 50.4 is the speed that we shot it up at. So that's a bear. There's a lot of algebra there. We got one more thing to do. The second part of the problem was find the maximum height of the ball. That part's going to be easy. So I'm going to take this off, and we'll finish this up by finding the maximum height. What do we need to know to find the maximum height? The vertical component of the velocity. So draw down our vertical. We need to know that vertical component. Yep. So we'll say sine 34 equals V over 50.4. So V equals sine 34 times 50.4. So if we do that, .18. That's our initial vertical velocity, right? From here on out, if we're trying to find time, well, we're trying to find a max height here. That's the initial vertical velocity. What's our final velocity at our maximum height? 0. Our acceleration, negative 9.8. We're trying to find delta x. Now we haven't found the actual time yet. So what equation would probably be the easiest if we just want to do this in one step? But we don't know that, we don't know the time to do that 1/2 one. Yeah.
How'd you find it?
The 28.18?
You can find time. Can't we use the equation we had earlier that was V sine 34 and 4.9?
Yeah, we could. We could.
You can find it.
Yeah, we could find the time, but I would say this is easier. This 28.18 was just the vertical component of this.
How'd you find it?
I took sine of 34, and then I just solved it for V. All right, so I think the easiest equation to use here, unless we wanted to do 2 steps, is just use this one. VI squared equals VI squared plus 2A delta x. We're trying to find the vertical displacement. So we're trying to solve for delta x. So just subtract that out. VF squared minus VI squared all over 2A equals delta x. So make a little space over here. So our final velocity is 0 at our maximum height, minus our initial velocity squared, all divided by 2 times negative 9.8. So let's see, 28.18 squared divided by 6. So yep, we get 40.5. So our displacement, 40.5 meters. That's the highest point that the ball makes it to before it comes down. All right, questions on that? Oh yes, we will. Tomorrow on the quiz we'll have one like that.
We have to remember that experience.